Hello and welcome here to Ars Electronica Home Delivery. Today's talk will be inside Futurelab. I'm not standing inside the Futurelab, I'm standing here inside of the Ars Electronica laboratories. Why I'm not inside the Futurelab? Because today we will talk about robotic origami, and some of these artworks we will talking today about are part of the exhibition here. You can see it here. These wonderful origamic structures are one example what we can show during the whole year here in the Ars Electronica Center. Inside Futurelab today is really a special try for us as well, because we have the key researcher from the Futurelab not here in person, because he's sitting down under in Australia. Hello, Matthew, can you hear me?
Yes, I can, Christoph. Good evening, or good afternoon to you.
Good afternoon, wonderful. Good evening to Australia. So this is really one of our first tries in this a little bit complex structure. So I have my Skype headphones here. I talk to Matthew and we see it here on our screen. So this will be really some kind like an experiment, but hopefully it will be fine. And of course, again, you can post your comments, your questions in our YouTube channel onto the YouTube commentary, and then we will, of course, answer your questions after the talk. Today's talk is about Oribotics, the art and science of robotic origami, and Matthew Gardiner, he's the key researcher in the Ars Electronica Futurelab, and his topic is robotic origami. And no more words to say. Matthew, your stage, your presentation. I'm really looking forward to get a little insight of this fantastic project, what you created the last years. Matthew, your stage.
Thank you, Christoph. So can we start with the first slide, please? So I'm going to talk a little bit about robotics and origami, and I'm starting with origami because this is the primary art form that I study, and it's the study of folding paper. So the word origami is a Japanese word that literally means fold paper. Next slide, please. So our work examines the natural language of folding. And so this is about how and where do we find folding and unfolding in nature. Next slide. So in the nature of folding, we find a lot of dualities. So things that have two sides. Origami is both an art and a science. So as a science, it's through mathematics and engineering. For example, origami is basically a geometric calculator. Just by folding a sheet of paper, you can solve divisions of area, lines, and angles very, very simply. As an art form, it's a creative sculptural form, one that uses one material and one operation to sculpt abstract, geometric, and complex expressive sculptures. Origami also forms a relationship between code and matter. As a language, origami can be used to transform matter in a programmatic way. So this links code and matter. Origami's main function as a mechanism is to expand and contract. And folding is the main mechanism that allows this to happen mechanically. Interior and exterior are philosophical ideas discussed by Deleuze as extensions from Foucault. To me, these ideas signify scale and the pleading of space. Next slide, please. Perhaps the most amazing thing about origami is scale. So origami occurs, or folding occurs, at all scales in nature, from protein folding at the nanoscale, to craft materials at the origami scale, to up to architectural materials at the interior. Going larger, geologists study the folding of tectonic plates and interactions of layers in the Earth's crust. In fact, the language of origami instructions uses the terms mountain and valley to describe the topological direction of folds. And going up even larger, some theories suggest that the shape of matter, some 85% of the unknown content of the universe, dark matter, can be expressed as the gravity folding a tessellated sheet. So the origami of the universe inspired one of the artistic research outputs from our work, and this is called the the folded geometry of the universe. Next slide, please. This is an image of the work. So, as I said, science theorizes that approximately 85% of the universe is dark matter. And one researcher, Mark Nenrink, suggested that it might be a tessellated sheet. Now, as an artist, I wasn't interested in expressing that directly or, copying his research verbatim. I was interested in asking a question: how could we imagine and sense something that's not only invisible, but can only be inferred by mathematics? So using folding as a metaphor, and in this case, unfolding is the expansion of time flowing forward. So I got very interested in the idea of what is expansion and what is contraction at a universal scale. And so I imagine this as a single moment in time and space that is partway through the unfolding shape of the universe, with time moving forward as expansion. So to contradict that, you could go backwards in time as reverse. So this is the reduction of folds and events back to nothing. So again, this is a static moment, a singular present of the folded geometry of the universe. Next slide, please. So our research is situated within artistic and scientific inquiry into folding, mechanisms, theory and algorithms, and in particular with robotics. And so when we combine robotics and origami, we get to a field called Oribotics. Next slide, please. So Oribotics began as a new term to describe my interest in folding and robotics. And like origami, with ori meaning fold, and kami meaning paper, in this case, the Oribot, the bot means robot. So conceptually, folding robot is what an Oribot is. And so I'm interested in the folded sheet, so the parts of the folded structures that you can see moving. So the mechanical structures that surround the bots are made to be as simple as possible to expand and contract the folding surface. So I made Oribotics to deal with the fascination I have for the movement of origami, the movement of folded surfaces. I mean, after all, origami making is a performance of moving paper through folds. So as time progressed, I began to think more about why these works are important to make. And I could start to imagine that a future needed folded structure. So generally, through this research, I've come to understand that origami could be the silicon chip and micro and nano engineering. Next slide, please. So it's very exciting now. We were awarded, the Ars Electronica Futurelab and myself as the principal investigator, were awarded a new project to continue our work. And this time, our previous work was to examine the language of origami, and this time we're interested in the art and science of robotic origami. So I'm going to talk a little bit about that now and what our aims are and what some of the works are that we're doing. So what we're trying to do is push forward the frontier of origami-based thinking. And because it's an art science grant, our aim is to extend knowledge from literature, and by this I mean scientific literature, into new practical tools and know-how for the studio. So I'm interested in what happens on the cutting edge in all fields that connect to origami and engineering and so forth, and bringing them back into artistic processes. Next slide, please. So there's a lot of prior work in this field. There's a lot of work in computational origami. There's lots of work in origami engineering. There's even new emergent fields called active origami. And some of the names that might have been in that were Miura, Maekawa, Kawasaki, Lang, Tachi, Domain, Mitani, Hao, Yu, Kurobayashi, and Kresling. That's not all of them, of course, but that's just a few of the contributors to this field of a kind of moving forward. And so our research agenda is to examine three topics: the idea of programming, the idea of transformation, and the idea of sensing. So next slide, please. So programming is about what I discussed earlier, the relationship between folding being used to define shape. But in this case, we're also interested in how it moves. And our aims in this area are to make computational origami joined with CAD tools to create some of the most powerful artistic tools for the field of Oribotics. So some of our sub-aims are looking at open source tools, we're looking at community collaborations, and we're interested in a design pipeline that goes from form to function and to fabrication. So one of the ideas that we came up with in our previous work was an experiment in this area, and we called it fold mapping. And so we're interested in how it opens up new areas of research into irregularity and exploring the limits of what we called natural folding syntax. So these are folds that occur naturally in nature. So this is something that we've discussed in some of our publications. So next slide, please. So fold mapping is basically a computational tool that lets us kind of sculpt with origami patterns. And these patterns that you see are part of what we determine as the syntax. It allows us to define the shape. In this case, what you're seeing on screen is just a flat plane, but what we're also able to sculpt is, the resolution of the folded pattern, the scale and the dimension and the shape of the pattern, and all of these get eventually outputted to the flat folded surface. So here's an example you can see on the right-hand side, this flat sheet of this very simple pattern that's been folded and been sculpted in 3 dimensions and unfolded. Here's another example of quite a nifty mechanism. This mechanism was discovered by Britta Kresling, and the Kresling mechanism is basically a cylindrical mechanism that, for a certain range of its operation, doesn't change the diameter of the cylinder, but expands and contracts. This is a sculptural object that I was working on during the research project, the previous research project, and you can see here that I'm able to define the shape, and I'm flipping through folding patterns. I'm examining from all sides, different aspects of the folding pattern, seeing what it might look like, getting a feeling for it, making a copy of it, and I'm about to put a part in the middle so that expands and contracts, somewhat like a clam mechanism might be. So something we could put air into and move backwards and forwards and open and close. So next slide, please. So the second point that we're looking at is transformation. So this is really looking at material intelligence, and the main active areas in this field already are active origami, and this is all about self-folding. So this is if you can combine materials in such a way that you, say, add heat, that the structure will fold up by itself. So you don't actually need to do any physical folding. And the other area is soft robotics. So this is the area we're probably most interested in because it involves repeatable actuation. Mostly in the case of active origami, we're looking at one-way or very slow mechanisms, or you need to be able to control the entire environment. So you need to be able to heat up or cool down entire space for the active origami to work. Whereas in soft robotics, you just need to use fluid, injecting fluid into basically a diaphragm or a kind of a balloon, an origami-shaped balloon that expands and contracts. And so this is one of the very, very interesting areas. And we're interested in making robust and repeatable actions. And we're also interested in printable soft actuators. Our ideal aim is to find the servo motor for origami actuators. So the servo motor allows a lot of simple controls in mechanics in general, but there's no equivalent currently for this angular movements that are very small and fit into the plane of a folded mechanism. So next slide, please. One of the things that we developed in the previous research that informs this research is a concept called fold printing. So fold printing is a process of using a 3D printer to print rigid panels onto flexible textiles. And so next slide, please. So this video you see here is our prototype, a large-scale fold printer, which we showed at the Ars Electronica Festival in 2016. We built a second prototype that has 2 printing heads. And what it does is basically move across a sheet of textile and print the areas where it shouldn't fold. And in this case, the white area is the textile. So that remains flexible. And so this is that same shape, it folded up. And what you see is that what actually you notice is, as an experienced origamist, the first thing I found was this material is incredible. It feels, it's flexible, It also has a rigidity, a robustness that paper doesn't have. And this is a really amazing find. And you see here, it also folds incredibly fast. So this is sped up, of course, about 1,000 times. But what we found is that compared to folding this same structure in paper, we found that this was about 5 times faster, which is quite a radical improvement just in shaping and in the ability to sculpt materials. So next slide, please. The next area we're looking at is sensing. So one of the questions we're asking in this area is what technology and fabrication techniques are required to create a seamless sensing interaction with a fold, so that the fold can be used as a device, as an implementation of a switch with both binary and continuous states. So this means that not only can it be used to switch something quickly on and off, but also to work in between, so using all the angular range of a fold, so as a continuous state. And so some of the work that we've done in this area has been, we did a few basic tests, and so this is the really interesting area for us, because if we can do angular sensing of not just one fold, but actually a whole fold network, we end up with quite a complex model of a geometry. So next slide, please. The two projects I'm going to talk about here are the OriSense, which was developed by Christoph Kiermaier, and it's a foldable pixel. So he made a conceptual prototype using the techniques that we developed in the research. And the other one is called the Accordion, and it's a prototype fold printed piano accordion. So next slide, please. Let's have a look at those. So as a co-researcher with us, Christoph eventually wrote his diploma thesis following the creation of this. So this is a Resch pattern that expands and contracts. And the idea is that this is nano-engineered, and it's a surface that bumps up to touch your finger and to make a button. This is the Accordion. So this is a fold printed piano accordion. Each one of the plates, you can't hear it, of course, in this video, but the interaction is that as you touch one of the plates, it replays back. What's interesting, however, is that you can use the folds and the adjacent plates to make connections. And so this performative surface is something that we're very, very interested in exploring in our current work. So going on to that, next slide, please. The topics that we're interested in examining all of these technical fields, what we're interested in the artistic, the additional artistic flavour is we're interested in things that occur on body. And we did work, actually I've got one of the samples that we did. You can be able to see this folded hat geometry that I'm wearing. Is this an example of on-body, but this is not as, we want to go further than making sculptural on-body fashion statements. We're interested in performative, musical, and we're also interested in things that are aquatic. So we're interested in finding the relationship between folding underwater. We're interested in these kind of fluid movements that could occur in these spaces. And that's because, next slide, please. To us, nature is an irregular continuum of materials and forces over time. So this is something that sort of an inspirational point. So this is the giant stairway in Ireland, and I was fascinated that this repeated structure from that occurs in the shapes there in the landscape. While it's not folded, it's an example of nature doing something repeatedly, but each time a little bit differently. And I think this is perhaps one of the powers and unique qualities that our methods have to be able to reproduce. So where most of the origami engineering is in regular, perfect kind of structures, we're interested in the irregular. We're trying to get to organic shapes through our work. And we feel this is a very important artistic distinction that we're making in our work. And so the next slide, please, Christoph. Thank you very much for listening and for watching so far. There are a few avenues that you can look into further. We've got a lot of published research. We've got work on the newly developed Futurelab site coming very soon. And all of the research that happened in this project that was funded by the FWF, thank you very much. It's their peak program is a fantastic contribution to the arts and sciences for Austria. And so all of the work you can find on orilab.art, all the publications and videos that we've published. And also you can find out more about my general practice on matthewgardiner.net. So thank you very much.
Thank you very much, Matthew. Great talk about Origami Robotics. I now have to change a little bit what I'm seeing here. And I try to put Matthew here on the big screen. Okay, Matthew, thank you very much.
Thanks.
Wonderful topic, really fascinating of what you are thinking of and how deep this research is going. There are some questions occurred here. What kind of materials do you use for your work? And did you start out with classical origami?
So I'll just backwards. Yes, I did start out with classical origami. As an 8-year-old kid, I picked up my first origami book in the library and haven't looked back. It's a fantastic art form that improves concentration, spatial recognition. There's all kinds of good things that happen when you start folding a piece of paper. Not to mention that it's also a kind of something that gives you a sense of patience and problem solving. In terms of materials, paper is where I began with Oribotics and with origami, but I soon found that if you fold a piece of paper, let's say you want to fold it 1,000,000 times over and over, it's going to break, probably after about 1,000 folds. And so I started looking at different polymers and different materials that could be used. Eventually I stumbled upon textiles, and it turns out actually that textiles are basically the originators of complex folded structures. If you go back in time, you'll find that textiles were made before paper, and textiles were pleated first. You see a lot of complex examples, especially in sort of neck pieces, and there's a lot of napkin folding occurred. And anyway, it goes way back, and it's also something that is very interesting to understand. This kind of global history of folding. It's not only Japanese in origin, it's actually occurred in countless places around the world.
Wonderful. And this, going to the next question, what was the most complex origami figure you ever created?
I think the most, well, I can say statistically speaking that some of the folded patterns we made in the last research project were the most complex in terms of they wouldn't have been able to be folded without using this technique. But in terms of classical origami, I do believe it was some works by some origami insects by Robert Lang. They are really tough, really challenging. There's a whole branch of super complex origami. The Melbourne Origami Group and myself once put together a super complex a Triceratops skeleton for exhibition in Melbourne some 25 years ago.
Okay, so really complex systems here. The next question is going deeper into combining. What was the greatest challenge in combining origami and robotics?
I think it was finding the patterns that would work in combination with the mechanism. There's a lot of beautiful patterns, a lot of amazing things, but for the mechanism, often the mechanism to actuate or to make it work would be bigger than the actual origami form, or too much bigger. And I think this was one of the first challenges I came across. Secondly, it was the understanding of the movement of patterns before, so designing them became a problem, which is a lot of the reason why the fold programming became such an active topic of interest, because I knew from experience this was a problem that's not readily solved or solvable using, common techniques.
I have a question here from our YouTube channel. How do you imagine the liquid environment and propulsion to interact with the folded object?
So there's several layers to this. One is that the liquid itself, like air as a liquid, I'm sort of cheating a little bit in the answer here, as air as a liquid injecting and in and out of the diaphragm is one way to create interactions. But what I've been imagining, and this occurs to me while I'm surfing and looking at reefs and so forth in Australia, and I noticed that there's a very directional movement of water. So this sort of tidal movements move in and out very, very directionally. And so this inspired me to think about what kinds of folding patterns could be anchored to a surface such as the ocean bed, and how might you design structures to allow the movements of water backwards and forwards to actuate these structures. So it's very much an imagined state at the moment. It's not realized work. So there are, of course, many layers to get to before you get there. But like most of this work, we start out with an endpoint, and then we make our journey on the way there.
On following question on this topic, you mentioned aquatic at the end of your talk. What do you mean by that? Some of your works already look like they live underwater.
Yes. So as I just explained in the previous answer, actually. So it's kind of covered a bit there. The aquatic sense I was referring to there is this fluid movement of water. But I'm actually also interested more so in creatures and things that live underwater. They have very, very, very interesting shapes and geometries, and they're also more otherworldly and less investigated than things that occur on the Earth's surface. And that's why I think it's an important area to investigate here.
Another question what we received here is, do you think you could make a robot out of an origami crane?
Actually, we did that.
Okay.
we did. Dr. Ogawa, another researcher in the Futurelab, actually came up with the idea to do this, and as part of our research work. And so I prototyped the process you need, and I actually have a printable pattern that you can use to make a crane, a soft robotic origami crane. And the difficulty with it is sealing the diaphragm. So making an airtight seal that works with the folded structure. So
can I download it somewhere? Can I download this?
No, we haven't published this pattern yet. It has been planned for some time to publish that with a kit on fold printing. So we'll make that a priority when our research kicks off.
Okay. And another question from YouTube. Are there any rules to create origami patterns to create structures from scratch? Because not all flat geometries work to create 3D shapes. Is there any algorithm or basic rule for it?
I would say there is no one rule. Rather, there is an increasing collection of algorithms and processes through which one can use to get to this point. Part of our work is to try and simplify some of this so that somebody could say I want this shape. I mean, there is one algorithmic method developed by Eric Demain and Tomohiro Tachi. It's called Origamizer, and if you feed this algorithm a three-dimensional model, it will try to generate a folded pattern for this shape. The complexity of that is that they're very, very difficult to fold. Traditional origami methods are actually much more efficient and much more direct for designing origami shapes. We're looking for a gap in between. We're looking that allows you to move to that shape from a flat surface or from an existing surface, so to allow you to expand or contract that surface to a larger or smaller area. And yes, for those purposes, there are developing algorithms, but there's no one rule per se. Okay. Rather, they're collections, yes.
Okay. Another question we got here is, I have heard of another term, robogami. How is this different, or is it the same like Oribotics?
Well, I think robogami is an interesting term, but to me, semantically, robogami means robo paper, and has more to do probably with the idea of making robots, like directly robots, whereas Oribotics places folding first. So the research is more fundamentally about folding. So it's more a difference of emphasis, though I do think that some researchers using the term robogami mean it in the sense that I mean Oribotics. But to me, it semantically doesn't make sense. I mean, when I was coining the term, I really thought, should it be robogami or Oribotics? And actually, it's about folding robots, not robot paper.
Okay. Origami seems like it has a lot of applications. How is it being used in other areas? Question from our stream.
Yeah, so there are two really amazing documentaries that answer this question very well, because there are a lot of applications. There's space applications, there's like compressing, there's aircraft applications for designing very strong and very lightweight aircraft structures. There are biomedical applications. So there was a heart stent designed that can go into the body very small and then expand using this active origami concept into a solid cylindrical structure. So this is quite an amazing area. And so the two documentaries are the Origami Code by Fact and Film, and the other one was Between the Folds by Vanessa Gould. And both these documentaries go into incredible detail with researchers from the past 10 years, and they look at all the different applications and all the different places and all the different ideas that have been revolving around computational origami and applications of this kind of applications of these ideas.
Okay, so there are these two documentaries. Are they available somewhere? Do you know this?
Yeah, can I post them to the stream at the end of the call? So I do believe some of them are available to stream via various services. You can definitely see the trailers for them on YouTube or on Vimeo.
Okay.
But whether I think Arte, the Origami Code was screened all across Europe as a documentary. It was produced for Arte.
A final question from YouTube. How and with which tools should a beginner start with computational origami?
Wow, okay. It's probably not a beginner field, but if you're interested in having a look at this, or what sort of, like, one of probably the best tools to get inspired by is Amanda Gassay developed an origami simulator. And this is very interesting because it's a simulation that allows you to put in an origami pattern, and what it will do is will fold it up for you. And it will show you what it might look like folded up. And so this is so using, sort of basic CAD tools or, flat 2D CAD tools, you could start drawing your origami pattern and then see what it might fold up like. And so this is probably the simplest combination of two tools that you could use. There are some great tools by Jun Mitani, and there's also some interesting work, very, very useful work by Tomohiro Tachi. So I can provide links to these again in the YouTube thread. Basically probably the simplest to use would be Jun Mitani's tools. He's got a program called Orirevo, which allows you to design cylindrical or revolutionary style objects.
Wonderful. So we don't have any question left. So thank you very much, Matthew, for this deep dive into origami robotics. And hopefully we see us soon here in Linz in person.
Yes.
And
absolutely we will. Yes.
I wish us here in Europe a good afternoon, in Down Under, good evening, and a good morning somewhere in the other fields of the world. Thank you very much, Matthew. And
thank you, Christoph.
Next week, Inside Futurelab will be again here out of the Ars Electronica labs, and we will focus more in the biological, biotechnological side, and there will another guest from the Ars Electronica Futurelab, Yoko, will make her talk about her research topic here next Tuesday at 1 o'clock Central European Time. Thank you very much for watching, and please stay tuned for Ars Electronica home delivery. Thank you very much.